AI engineer interview questions and answers. The questions you actually get, the weak answers most people give, and the strong answers that get you hired. I've shipped LLM systems in production and worked on AI engineering at companies you recognize. I know what these interviews are testing because I've been on both sides of them. So I'm going to give you the glossary version. I'm going to give you what actually gets people hired. If you search for AI engineer interview questions, you get a list like this. Define an LLM, define RAG, define fine tuning. You should absolutely know these cold, but on their own, they're not what's going to get you the offer right now. A real AI engineer interview goes deeper than definitions. They're not checking whether you memorize terms. They're checking whether you can build, debug, evaluate, and run AI systems that hold up in front of real users. Strip it down, and the interview is testing four things. Almost every question is one of these in disguise. One, can you code? Two, do you understand AI systems? Three, can you evaluate and debug behavior? Four, can you make it work in production? The line to remember, if you take one thing from this video, take this. AI engineering is software engineering plus AI systems. Both halves. The candidates who forget the software engineering half are the ones who get filtered out first. The fork, most candidates prepare by memorizing AI terms. The strong ones prepare by understanding systems. The gap shows up in the first 30 seconds of any answer, and the interviewer hears it immediately. So I'm going to take you through the questions you actually get roughly in the order they come up. For each one, I'll show you the weak answer most people give and the strong answer that gets you taken seriously. Same question, very different outcome. The pattern is easy to hear once you know it. A weak answer defines a term and stops. A strong answer explains the trade-offs, the failure modes, and how you measure whether it's working. A definition sounds like a textbook. Trade-offs sound like someone who's actually built the thing. And every question has a quieter question underneath it. When they ask what RAG is, they're really asking whether you've built what. When they ask about evaluation, they're asking whether you've had to trust this in production. Answer the question behind the question, and you always go deeper than the person answering the words. First question almost every time. What is an LLM? Or how does it work? It sounds basic. It's a filter. How you answer this sets the level for everything after it. The weaker answer is the one everyone gives. It's a model trained on a lot of text that predicts the next word, like ChatGPT. True and completely forgettable. It tells the interviewer you read the first paragraph and stop. The strong answer connects the mechanism to the consequences you deal with as an engineer. It's an autoregressive next token predictor. At inference, it generates one token at a time over a fixed context window. Latency comes from that because it writes sequentially. Cost comes from that because you pay per token. And hallucination comes from that because it's modeling likely continuations, not looking facts up. That last point is why you reach for retrieval and evaluation. What is prompt engineering? They're testing whether you treat prompts as part of a system or as a magic words. The weak answer is writing good prompts to get better answers. It treats the prompt like a lucky phrase you stumble onto, which is exactly the impression you don't want to leave. The strong answer is that prompt engineering is specifying the task precisely, controlling the output format, and giving the model examples when it needs them. The senior framing is that prompts are part of the system. You version them, you test them, and you run them against an eval set every time you change one. You treat them as code you can regress, not as lucky phrases you stumble onto. What is RAG? This is the most common question after the basics, and the one people answer most shallowly. Retrieval augmented generation. You give the model documents so it can answer questions about them. That's the idea, but it isn't a system. It's roughly the line you read on a marketing page. RAG means you retrieve relevant context at query time and put it in the prompt. So the model answers from your data instead of its training. The pipeline is the answer. You chunk your documents, embed them into vectors, and store them. At query time, you embed the question, pull the most similar chunks, often re-rank them, and feed the best ones into the model. Question 3, draw the pipeline. If you can sketch this out loud, calmly, end to end, you've already ahead of most candidates. The senior move is to say where it breaks because that's where the real work lives. Most RAG failures aren't the model, they're retrieval. Chunking that splits an idea in half, pulling too few chunks, or so many that the answer gets buried. No re-ranking, so the right chunk sits in position 20. I'd evaluate retrieval separately from generation because if the right context never arrives, no model can save you. Then we go to question 4, where you use RAG, fine-tuning, or just prompting. This is a favorite because the decision framework is the whole answer. The weak answer, fine-tuning, is when you train it on your data. RAG is when you give it documents. Both roughly true, and neither answers the actual question, which is when you choose one over the other. The strong answer, I think of it as a ladder, cheapest rung first. Start with prompting and examples. If the model needs knowledge it doesn't have, especially knowledge that changes, use RAG. Reach for fine-tuning when you need consistent behavior, format, or tone, or to make a smaller, cheaper model do one narrow job well. You only climb when the rung below stops working. And this is the mistake that ends interviews, fine-tuning to add facts. Fine-tuning teaches behavior, not knowledge. If you fine-tune to memorize your docs, it's expensive. It goes stale the moment the docs change and still makes things up. Knowledge that changes belongs in retrieval, not baked into the weights. Say that, and you sound like you actually shipped one. Question 5. What is fine-tuning, and how would you actually do it? The how is where people fall apart. The strong answer, fine-tune adjust the model's weights on your examples so it behaves in a certain way by default. In practice, you rarely retrain the whole thing. You use parameter-efficient models like LoRA, where you train a small set of extra weights and leave the base model frozen. It's cheaper, it's faster, and you can swap adapters per task. Knowing that one detail signals you've done it, not just read about it. Question 6. What is a vector database, and how does similarity actually work? The weak answer, a database that stores vectors and finds the similar ones. Correct, and it stops right before everything that matters. It doesn't show you understand how or when you even need one. The strong answer, embeddings turn text into vectors where similar meanings sits close together in space. A vector database finds the nearest ones fast using approximate nearest neighbor search, something like HNSW, which gives up a tiny bit of recall for a huge speed gain at scale. The senior note is that you don't always need one. For a few thousand documents, you can hold the vectors in memory and skip the infrastructure. You add the database when scale forces you to. Question 7. What is an agent, and how would you build one? Agents are the buzzword, so the shallow answers come fast here. The weak answer, an AI that uses tools and completes tasks on its own. It's the demo description. It says nothing about the parts that make agents hard to actually run. The strong answer, an agent is a language model in a loop. It decides on an action, you run the tool, you feed the result back, and it decides again until it's done. The interesting part is the reliability, which is exactly what a demo hides. You need stopping conditions so it doesn't loop forever, error handling for when the tool fails, and a tight budget because every step pays for the full context again. And the most senior thing you could say here is that you often choose not to use an agent at all. If the steps are known ahead of time, a fixed workflow is cheaper, faster, and far easier to debug. You reach for an open-ended agent only when the path genuinely can't be planned in advance. Reaching for one by default is a junior instinct, and good interviewers are listening for exactly that. Quick aside, if you want to actually build the systems behind these answers, not just recite them, that's what I train developers for inside AI Engineer Launch. I teach the full AI engineering path, and I've got recruiters working round the clock to put my people in front of the right roles and land that first AI job. The link's in the description if that's you. Back to the questions. Where offers are won and lost. Everything so far most prepared candidates can stumble through. The next set is different. These are the production questions, and most people have never had to make AI work for real users. This is where the offer is actually decided. Question 8, the big one. How do you evaluate an LL system? If you could only ask one question, it would be this one. It's the single clearest signal of whether someone has shipped or only studied. The weak answer, you check whether the answers look good. That's the answer of someone who has never had to defend the system to anyone. There's no rigor in it, and the interviewer knows immediately. The strong answer, you can't skip when you can't measure. So you build evals. For a task with the right answer, you keep a test set with reference answers and score against it. For open-ended output, you use a model as a judge with a clear rubric plus human spot checks. You run that suite every time you change a prompt or swap a model. In a RAG system, You evaluate retrieval and generation separately because they fail for different reasons. Question 8, what you measure. And when they push on what you measure, you don't say quality and stop. You name the dimensions. Is the answer faithful to the source? How accurate is it against the reference? What's the latency? What does it cost per query? A real eval scores more than one thing because in production, all of them matter at once. Question 9, a user got a wrong answer. How do you debug it? They want to see your process, not a guess. The strong answer? First, I reproduce it with the exact input. Then I look at what the model actually received, the full prompt and context, not what I assumed it received. In a RAG system, the bug is upstream most of the time. The right chunk was never retrieved. So the model never had a chance. I trace the pipeline backward from the bad output until I find the step that broke. Then I add a test so it can't come back. Question 10. How do you handle hallucination and make the system reliable? They're testing whether you think you can eliminate them or whether you know better. The strong answer, you can't eliminate hallucination, so you contain it and measure it instead. Ground the model with retrieved context and ask it to cite sources. Constrain the output to a schema so it can't freestyle. Validate the result and retry on failure. For anything high stakes, keep a human in the loop and put a number on it with evals so reliability is something you track, not something you hope for. Question 11. How would you control cost and latency in production? This is where understanding tokens pays off directly. The strong answer, route the simple high volume work to a cheap model and save the expensive one for what truly needs it. Cache the stable parts of your prompts, batch anything that doesn't need an instant answer, cap output length because output is the slow, expensive half, and measure cost per successful task, not cost per token, because a cheap model that needs 5 tries isn't cheap. Question 12. How do you deploy an LLM app to production? They want to know if you've run one or built one on your laptop. The strong answer? I treat the model like any other unreliable external dependency. Retries with backoff, a fallback model when the primary is down or rate limited, streaming so the experience feels fast, hard timeouts and budget caps, and monitoring on the things that actually drift, cost, latency, and answer quality, not just whether the server is up. Question 13. How do you handle security, like prompt ejection? A year ago, this was rare in interviews. Now comes up constantly. The strong answer? I assume anything the model reads could be hostile, including retrieved documents and tool outputs. So I never let model output trigger a dangerous action without a check. I give every tool the least privilege it needs and keep sensitive data out of the prompt unless it has to be there. Prompt injection is the new version of trusting user input, and the fix is the same as old instinct. Don't. Now, the part candidates are generally surprised by. There's usually still a coding interview. People assume an AI role means you just call an API and write clever prompt. The good companies know better, and they check. Why the coding is real? Remember the line, AI engineering is software engineering plus AI systems? The company is still hiring an engineer. They need to see that you could write clean code, reason about data structures, handle APIs and failures, and write a test. The AI doesn't replace any of that. It sits on top of it. The coding is usually practical and close to the job itself. Write a function that chunks a document sensibly, implement top K retrieval over a list of vectors, build an API client that retries and respects rate limits, write a small evaluation harness. It's the plumbing of a real AI system, and you should be able to write it without thinking hard. And yes, classic data structures and algorithms still appear, especially at the larger companies. Not because you'll balance a binary tree on the job, but because it's still the fastest way to confirm you can program under pressure. If you're targeting those companies, prepare for both tracks, the AI systems questions and the algorithm round. A realistic task, this is the kind of thing you might be asked to write live. Nothing exotic, clean, correct, and you talk through it as you go. What separates people here is talking while you work, not raw speed. State your assumptions. Name the edge cases, an empty input, a tie, a list too big to hold in memory. Write the test. Mention the trade-offs you're making. That narration is the point. They're hiring the thinking out loud, not just the lines of code. Sometimes the coding is a take-home instead. The rules don't change. Treat it like production code and tests. Write a short README. Include a note on the trade-offs you made and what you do with more time. A clean take home with evals be the clever one without them, every single time. The categories that reveals the most. The last big category is system design, and it's where senior thinking shows the most. They hand you something open-ended. Design an AI assistant over our internal docs. Design a system that answers customer questions. There's no single right answer. They want to watch how you think. So system design, the first move. The first move is the most important, and most people skip it. You don't start drawing boxes, you ask questions. How many documents? How often do they change? How many users? How fast does it need to respond? How accurate? What's the budget? The requirements decide the design. Jumping straight to a vector database tells them you pattern match instead of thinking. Then you walk the pipeline out loud. Ingest, chunk, embed, store. At query time, retrieve, re-rank, generate. Around all of it, evaluation and monitoring. Walking that end-to-end calmly is most of the battle. At every box, you name the trade-off out loud. Bigger chunks keep more context, but cost more and can vary the answer. More retrieved chunks raise recall, but raise cost and latency. A bigger model is more accurate, but slower and pricier. You're not hunting for the perfect choice. You're showing that you see the choice at all. Then you close the loop they're really waiting to hear. How does this break? And how would I know? Retrieval misses. The model contradicts the source. Cost runs away under load. And how would I measure success? Faithfulness to the documents, latency, cost per query, user feedback. Naming failure and measurement is what separates a designer from someone who's just describing a diagram. Put together, a strong answer sounds like this. Clarify the scale and the latency target. Chunk and embed the docs into a vector store. Retrieve and re-rank per question. Generate with citations. Evaluate faithfulness offline and monitor cost and quality in production. 2 minutes, calm, end to end. That is a senior answer whether or not your title says senior. A lot of you watching aren't senior yet, and you don't have to be. You just have to answer it like someone who thinks about systems. There are 4 habits that do almost all of the work, and any of them can be the thing that moves you up a level in the interviewer's head. First, talk in trade-offs, not absolutes. A junior answer says this is the best tool. A senior answer says it depends, then names the factors worth weighing. That phrase, it depends, followed by the actual factors, is one of the strongest things you could say in any of these interviews. Second, bring up evaluation and failure modes before they ask. When you describe the system and how you would test it and how it might break without being prompted, the interviewer mentally moves you up. Most candidates never mention either one, so doing it unprompted stands out immediately. Third, talk about cost, latency, and what happens under real load. Anyone can make something work once in a notebook. Mentioning what it costs at scale, how it behaves when it's slow or failing, tells them you thought past the demo and into the part of the job that's actually hard. Fourth, have one real story ready. Something you built, what went wrong, and what you changed. It doesn't have to be big. A weekend project where retrieval was useless until you fixed the chunking beats any definition you could recite. Real beats rehearsed every time. The candidate you're trying not to sound like is the one who only watched tutorials. They define every term correctly, they name all the popular tools, and they describe the happy path where everything works. Then they go quiet the moment you ask what happens when it doesn't. There are tells the interviewer is listening for. Saying a tool's name as if it counts as an answer, describing only the version where nothing fails, never once mentioning cost, latency, or evaluation. If your answer would survive being copied straight off a landing page, it's too shallow. Add the part that only shows up after you actually run the thing. And when you hit something you don't know, say so, then show how you'd figure it out. I haven't used that specific tool, but I'd approach the problem like this. Is a strong answer. Bluffing is the safest way to lose a senior interviewer because they can tell and they doubt everything else you said. One more almost nobody prepares for. At the end, they ask if you have questions. That's still part of the interview. Ask how they evaluate their AI systems. Ask what breaks most often in production. Ask where the cost goes. Those questions show you think like an engineer, and they tell you whether the team actually knows what they're doing. Step back from all of it, and the job is one thing. They're hiring someone who can take these powerful but messy models and turn them into systems that are correct enough, cheap enough, and reliable enough to put in front of real users. Every question in the interview is just a different angle on that one ability. And if you're coming from another engineering background, that experience is an advantage here. knowing how to debug, how to think about cost, how to run something in production, how systems fail, all of it transfers directly. And the AI part is new. The engineering discipline underneath it is exactly what these interviews are testing, and you may already have most of it. And to put one fear to rest, because it comes up constantly, you do not need a PhD for this. These are not research interviews. Nobody's asking you to derive the math or invent a new architecture. They're asking whether you can build and run systems on top of models other people train. That's engineering, and it's learnable. So if you actually want to prepare, don't memorize the glossary, build something small and real, a RAG system over your own notes, then break it on purpose, watch it fail, and fix it. Everything you learn doing that is exactly what these questions are testing, and you'll be able to talk about it because you lived it. If you take one habit into every answer, make it this. After you define something, explain the trade-off and how do you measure it. That single move turns a textbook answer into an engineer's answer on every question they can throw at you. So this is what it all comes down to. The candidate who only defines terms sounds irreplaceable. The one who explains systems, trade-offs, and failure modes sound like someone they need. Same questions, completely different offer. If you want to walk into these interviews able to answer like that, because you've actually built the systems, that's the whole reason I built AI Engineer Launch. I train developers in the real AI engineering stack, the things companies are hiring for. And I've got recruiters working round the clock to get people in front of the right roles and land that first AI job. If you're ready to make that move, the link is in the description.